Hello everyone, and welcome to our presentation. Today, we'll be exploring fixed film secondary treatment, an essential part of wastewater management. The focus will be on how these processes help clean our water before it returns to the environment. We'll cover the main types of secondary treatment, particularly trickling filters and rotating biological contactors, or RBCs. I'm excited to share how these biological technologies work to break down organic matter and improve water quality. So, let's get started and dive into the details of these fascinating treatment methods. Let's take a moment to understand what a trickling filter is. Essentially, a trickling filter is a type of biological treatment system used in wastewater treatment. Most of these systems are designed as large, shallow, cylindrical structures. Picture a big, round tank that's not very deep, often filled with media like stones or plastic. These media serve as the surface where bacteria and other microorganisms can grow and break down organic matter in the wastewater. At the top, you'll find an overhead distributor that evenly spreads the wastewater over the media surface. Now, depending on the type of media used, the design can vary quite a bit. If natural media like stones are used, the filter tends to be shallow because stones don't pack tightly. But if synthetic media, such as plastics, are utilized, the towers can be much deeper, sometimes reaching 15 to 30 feet in height, allowing for a larger surface area for biological activity. This flexibility in design helps optimize the treatment process based on the specific needs of the system. Overall, understanding these variations and the structure of trickling filters is key to appreciating how they effectively treat wastewater through biological processes. Let's take a closer look at the trickling filter components. Starting with the inlet system, this is where the wastewater enters the filter. It's designed to convey the water smoothly through inlet pipes and distributor arms. These arms have adjustable orifices, which are important because they help ensure the wastewater is evenly spread across the entire filter media, maximizing treatment efficiency. Next, we have the filter media itself. This is really the heart of the biological process. The media provides a large surface area where beneficial microorganisms can grow. These are the slime layers that break down organic matter. The depth of this media varies depending on the material. For rock, it's typically between 3 and 8 feet, whereas synthetic materials can go much deeper, from about 15 to 30 feet. The choice and depth of media are crucial for optimizing biological activity. Moving on to support and drainage, this component includes support grills that hold the media in place securely. Beneath that, the underdrain system plays a vital role. It collects the treated water as it percolates through the media and also allows air to flow through the media. This airflow is essential because it helps maintain aerobic conditions, which are key for effective biological treatment. Finally, the outlet system gathers the treated effluent through outlet boxes and pipes. It regulates the flow of water leaving the filter, ensuring it moves smoothly into the next stage of treatment. All these components work together seamlessly, embodying the core principles of biological wastewater treatment, which is both efficient and sustainable. Let's take a closer look at how biological treatment actually works. Now, the term filter might make you think that solids are being strained out, but that's not quite what's happening here. Instead, as wastewater passes through the media, a fascinating biological process occurs. A gelatinous coating, known as a zoogleal film, forms on the surface. This is made up of bacteria, protozoa, and other tiny organisms. This film is incredibly important because it absorbs and uses organic matter that's suspended, colloidal, or dissolved in the water. So, as the wastewater flows over this film, the organisms feed on the organic material, effectively breaking it down. They use this organic matter as food, turning it into new biomass and energy. This process also involves oxidation, where organic material is converted into carbon dioxide and water, thanks to the dissolved oxygen present in the water. And just like any living system, there's a natural cleanup process. Excess biomass, or the growth that's no longer needed, sloughs off and washes away with the effluent, leaving the system ready to continue treating incoming wastewater efficiently. This entire process is a key part of biological treatment, helping us remove organic pollutants naturally and effectively, and it ties directly into the overall goal of improving water quality. Let's talk about the critical role of ventilation in our systems. Why does airflow matter so much? Well, for oxidation processes to work effectively, the biological film needs a steady supply of dissolved oxygen. This oxygen is absorbed from the air that's circulating through the filter voids, those spaces between rocks or media. Without proper airflow, these voids can become clogged, which causes operational problems like ponding and a significant drop in efficiency. Now, looking at the different types of media, synthetic media, which is typically plastic, has a high void space, about 95%. This large void space allows for high loading rates, meaning it can handle more biological activity without choking. On the other hand, natural stone media like rocks has a smaller void space, around 35%. This limits the loading capacity, so it's less efficient in terms of biological film growth and oxygen transfer. So, ensuring adequate ventilation and understanding these differences in media are key to maintaining optimal system performance and avoiding issues down the line. Recirculation plays a crucial role in boosting the efficiency of trickling filters. By recycling the filter effluent, we allow it to make multiple contacts with the biological film, which really enhances the treatment process. This increased contact time helps the microorganisms do their job more effectively, leading to better breakdown of organic matter. Additionally, recirculation seeds the lower parts of the filter with active organisms, ensuring a more uniform biological activity throughout. It also promotes more continuous slewing of excess growth, which helps prevent clogging and maintains proper filter function. Another key benefit is preventing ponding. When flows are higher, the system can handle the volume more evenly, causing uniform slewing of excess biomass. This prevents excessive buildup of material, which could otherwise block airflow and reduce oxygen transfer. As a result, ventilation through the filter improves, supporting healthier biological activity. Recirculation also aids in controlling pests. When hydraulic loads are increased, it reduces the chances for snails and filter flies to breed, since their habitats are disrupted by the consistent flow and reduced stagnant areas. Furthermore, it helps dilute the wastewater BOD, or biological oxygen demand. This dilution prevents excessive accumulation of organisms on the media surfaces, keeping the system balanced and preventing overloading. Finally, during periods of low flow, recirculation keeps the distributors moving. This prevents the growths on the filter from drying out or freezing, ensuring continuous operation and protecting the system from damage. Overall, recirculation is a vital tool for maintaining optimal performance and stability in our treatment process. Now, let's take a closer look at how trickling filters are classified based on loading, which is essential for understanding their design and operation. First, we have the concept of hydraulic and organic loadings. Hydraulic loading refers to the total liquid volume, including recirculation, expressed in gallons per day per square foot of filter surface area. This helps us quantify how much liquid is passing through the filter relative to its size. Organic loading, on the other hand, measures the pounds of BOD, biochemical oxygen demand, applied per day per 1,000 cubic feet of filter media. This indicates how much organic matter the filter is processing. Moving on to the types of filters, we start with the standard rate filters. These typically handle hydraulic loadings between 25 and 100 gallons per day per square foot and organic loads of 5 to 25 pounds BOD per day per 1,000 cubic feet. They usually use rock media about 6 to 8 feet deep, and their effluent has a stable BOD level of around 20 to 25 milligrams per liter. Next, we have high-rate filters, which are designed for higher loads. They can handle hydraulic loadings ranging from 100 to 1,000 GPD per square foot when using rock media, and even higher when synthetic media, up to 2,100 GPD per square foot. Organic loads are also higher, ranging from 25 to 100 pounds BOD per day per 1,000 cubic feet for rock media, and 50 to 300 pounds for synthetic media. These filters typically use rock or synthetic media that are about 3 to 5 feet deep, and they tend to produce more uniform slewing of the biomass. Finally, roughing filters serve a different purpose. They handle very high organic loads, often 100 to over 300 pounds BOD per day per 1,000 cubic feet. Their main goal is to reduce the load on subsequent treatment processes, especially when dealing with strong industrial wastes. They can remove about 50 to 70% of BOD, which helps protect the downstream systems from overload. Understanding these classifications helps us select the appropriate filter type based on the specific wastewater characteristics and treatment goals. When we talk about filter staging configurations, it's important to understand that the number of filter stages needed really depends on several key factors. These include the size of the plant, the flow rates of wastewater, the strength of the wastewater itself, and the quality of the effluent we're aiming to achieve. For smaller facilities with moderate wastewater strength, a single-stage filter system often works quite well. It's simpler, cost-effective, and usually sufficient to meet treatment goals. However, when dealing with larger plants or more demanding water quality standards, a two-stage system tends to be the preferred approach. In these setups, filters are arranged in series, which means the water passes through multiple filtration steps. Sometimes, you'll see a secondary clarifier placed between these stages. That's to help improve water clarity and quality further. Recirculation is almost universally practiced in two-stage systems. This means some of the filtered water is fed back into earlier stages, enhancing overall efficiency and ensuring better removal of contaminants. Understanding these configurations helps us optimize the treatment process for different plant sizes and treatment goals, aligning with our overall aim of effective and sustainable wastewater management. Let's talk about why trickling filters are such an excellent choice for secondary treatment. They are known for being one of the most trouble-free options out there. Unlike some other treatment processes, they require less ongoing attention and control, making them more manageable overall. When recirculation is involved, they tend to handle shock loads better, with fewer difficulties and quicker recovery times. Think of the filter like a sponge. It soaks up and treats large amounts of BOD quickly, without causing severe upset to the system. However, it's important to note that suspended solids in the effluent can cause water to become turbid. So, even if there are shock loads, the poorer quality water might not be immediately visible because of this turbidity. Overall, trickling filters are a reliable, efficient, and resilient choice, especially when considering operational simplicity and quick recovery from disturbances. Let's talk about troubleshooting ponding in your filtration system. Ponding happens when the open area in the filter gets blocked or filled, causing water to collect on the surface and form ponds. This is often due to excessive organic loading that isn't matched with enough recirculation, or issues like poor primary clarification, which fail to remove debris early on. Other common causes include using media that's too small or uneven, buildup of fibers or trash, and an overgrowth of insect larvae or snails. To address ponding, one effective method is using a high-pressure spray to break up surface accumulation. Think of it as giving the filter surface a quick rinse to clear out the debris. Manual agitation is another approach. You can turn or stir the surface with a rake or fork to remove leaves and debris. Chlorine dousing is also helpful. Applying about 5 mg/L of chlorine for several hours can control unwanted growth on the surface. Flooding the filter, meaning submerging the media completely for about 24 hours, encourages growth slewing, which helps clear out organic buildup. Lastly, drying out the filter by shutting off flow for a few hours allows any remaining growth to dry and detach naturally. These techniques are all about restoring proper flow and preventing ponding from disrupting your filtration process. Let's talk about managing odors and filter flies in trickling filters. First, odor control. Since these filters operate aerobically, you generally shouldn't encounter serious odors unless there are high concentrations of odor-producing compounds. If you do notice foul odors, it usually indicates anaerobic conditions, which we definitely want to avoid. To keep things running smoothly, it's important to maintain aerobic conditions throughout the collection system and primary units. Checking the filter ventilation is key, as well as increasing the recirculation rate if needed. Also, making sure wastewater splash is contained within the filter helps prevent odors from escaping. Now, onto filter fly management. The Psychota filter fly is quite tiny and prefers environments that alternate between wet and dry. Controlling these flies involves several strategies. For example, increasing the recirculation rate can help, especially since synthetic media may require higher hydraulic loadings or even weekly flushing. Keeping orifice openings clear is also crucial. Applying approved insecticides carefully to the filter walls can help, but should be done cautiously. Flooding the filter for about 24 hours at intervals shorter than the fly's 7-day life cycle can significantly reduce their population. And finally, good housekeeping practices are essential. They help eliminate fly sanctuaries and prevent infestations. All these measures are interconnected, and by managing odors and flies effectively, we ensure the overall health and performance of the treatment process. Now, let's talk about cold weather operations and how we can manage wastewater systems effectively during colder conditions. Generally, cold weather doesn't cause major issues for wastewater in pipes or clarifiers. However, there are certain areas where problems can arise, such as when wastewater is sprayed from distributor nozzles or exposed in thin layers on media surfaces. In these situations, there's a risk of freezing, which can lead to ice buildup on the filters. While icing can reduce filter efficiency temporarily, it's important to keep the units running. Maintaining continuous operation helps preserve effluent quality and prevent structural damage caused by ice expansion. To minimize issues, we can reduce recirculation flow rates, but it's essential to still maintain enough flow to keep the filter functioning properly. Operating two-stage filters in parallel instead of in series can also help because it reduces the exposure of the media to cold conditions. Adjusting the spray pattern by modifying or removing orifices and splash plates can cut down on unnecessary spray and heat loss, which is another effective strategy. Additionally, physical protection measures like wind screens, covers, or canopies can significantly reduce heat loss from the system, helping to keep components warmer. When ice does form, especially in larger areas, it's often necessary to physically break up and remove the ice buildup to restore proper operation. Overall, these measures help us keep the treatment process stable and effective, even in cold weather, aligning with our goal of maintaining optimal system performance year-round. Let's talk about some essential maintenance procedures that keep our equipment running smoothly. First up, bearings and seals. It's really important to monitor the oil weekly, paying close attention to the level and condition, because this directly impacts the lifespan of our equipment. Keep an eye out for water contamination, which can cause damage, and make sure the sensing lines are not plugged. When it comes to oil, I recommend using turbine oil that contains oxidation and corrosion inhibitors to protect the components. Also, if you're replacing mercury seals, switch to modern alternatives since mercury is toxic and poses environmental hazards. Moving on to distributor arms, always remember to work on the orifices only after the arms have completely stopped moving. To keep them clean, perform a weekly flush by opening the end dump gates. Don't forget to clean debris daily and clear the orifices as needed. Adjust the turnbuckles to maintain the proper level of the arms. This is key to smooth operation. For larger distributors, normal rotation speed is about 1 RPM. Any faster than that can cause damage to the bearing races, so keeping a steady, moderate speed is crucial. Lastly, let's cover underdrains. These are buried beneath the filter bed, so regular maintenance is vital. Use clean-out flusher branches to remove sludge deposits or debris that might accumulate. Consider borrowing high-velocity cleaners from the collection system maintenance team. They can really help clear out stubborn deposits. I recommend scheduling this cleaning every 3 to 6 months to ensure the underdrain system stays open and free of obstructions. Consistent maintenance like this is key to preventing costly repairs and keeping our system functioning optimally. Let's start with safety first. It's absolutely crucial to prioritize safety whenever you're working around filters and distributors. First, always remember to stop before you begin work. This means you should turn off the flow to the filter and make sure the distributor has completely stopped rotating. It might seem like a small step, but it's vital because the arms of the distributor can generate a force comparable to a large truck. If you attempt to work on it while it's still moving, serious injuries can happen. So, taking that moment to shut everything down properly can save you from potential harm. Next, let's talk about watch your step. The surface of filters can become extremely slippery because of slime growth. This slime makes it easy to slip and fall, which can lead to injuries. That's why I recommend wearing rubber boots with deeply ridged soles. These provide better grip and stability. When walking on the filter media, take extreme care, slow down, pay attention, and make sure your footing is secure. And a quick safety tip: never carry or use glass containers on the media surface. Glass can easily break, creating a hazardous situation. Overall, these precautions are about protecting yourself and making sure you can work safely and efficiently. Remember, safety isn't just a rule, it's a responsibility we all share to keep ourselves and our coworkers safe. Rotating biological contactors, or RBCs, are a really interesting secondary treatment option for both domestic and biodegradable industrial wastes. The core of the system involves a rotating shaft that's surrounded by plastic discs, which we call media. Together, the shaft and these discs form what's known as the drum. Now, when the conditions are just right, a layer of biological slime, or biofilm, develops on the surface of these discs. This process is actually quite similar to trickling filters, where biological slime grows on rocks or other media. But in the case of RBCs, the slime grows specifically on the plastic discs. As these discs rotate, the slime is periodically brought into contact with settled wastewater. This allows the microbes to digest organic material effectively. Then, as the discs continue to turn, the slime is exposed to the atmosphere, gaining oxygen that's vital for their metabolism. So, in essence, RBCs harness the natural growth of biofilms on rotating surfaces, providing a continuous process that promotes efficient biological treatment. This method is quite effective because it maximizes contact between the microbes and the wastewater, making it a valuable part of the overall treatment process. Let's take a closer look at the RBC system components and how they work. The core of the system is the plastic disc media, which are made from high-density plastic. These discs are quite large, usually about 12 feet in diameter, and they are bonded together and assembled onto horizontal shafts that can be up to 25 feet long. The spacing between each disc creates void spaces that allow for effective distribution of wastewater and air throughout the system. As the media rotate at approximately 1.5 revolutions per minute, about 40% of their surface area is immersed in wastewater at any given time. This rotation is crucial because it ensures that the media gradually come into contact with the wastewater and the biological slimes on the discs. When the discs turn, they pick up a thin layer of wastewater, which then flows over the biological slimes. This process promotes the breakdown of contaminants in the wastewater, making the system highly efficient. Understanding these components and how they operate helps us appreciate the innovative engineering behind the RBC system and its effectiveness in biological treatment. Let's take a closer look at the RBC process flow. Typically, RBC processes are divided into 4 distinct stages. These stages are separated by removable baffles, concrete walls, or cross-tank bulkheads, which help organize the flow of wastewater. Now, the flow of wastewater can happen either parallel or perpendicular to the shaft, depending on the design. Each of these bulkheads includes an underwater orifice. Think of these as controlled gateways that allow wastewater to pass from one stage to the next, ensuring the process moves smoothly. This staged approach is really important because it maximizes effectiveness. In the first stage, the media is exposed to high BOD levels, meaning the organisms here work vigorously to reduce BOD at a high rate. As the wastewater progresses through subsequent stages, the BOD levels decrease. This naturally causes a drop in removal rates, but it's also where nitrification begins to take over. This staged setup is key to optimizing overall treatment efficiency, aligning perfectly with our goal of understanding how biological treatment processes are designed for maximum performance. Let's take a closer look at observing RBC media health. First, a healthy appearance typically shows a brown to gray color, with no algae present. The media should have a shaggy look with uniform coverage and very few bare spots. Importantly, there should be no offensive odors, indicating everything is functioning properly. Now, if you notice a black appearance, that's usually a sign of solids or BOD overload, which often leads to low dissolved oxygen in the effluent. To address this, the solution is to place another RBC unit in service or pre-aerate the influent to boost oxygen levels and reduce solids buildup. When the media appears white, it indicates sulfur-loving bacteria are active, usually during high-loading conditions. This can also happen if there are industrial discharges containing sulfur compounds. The remedy here is to add an additional RBC unit or pre-aerate to help manage the sulfur compounds and maintain healthy microbial activity. Finally, severe sloughing happens when toxic or inhibitory substances are killing off the organisms. This is a sign of compromised media health. To fix this, you need to eliminate the toxic substances, dampen loading peaks, and maintain a diluted, uniform concentration to support healthy microbial communities. Overall, regular observation of media color, appearance, and sloughing helps us ensure the system remains healthy and operates efficiently. Let's now discuss some common issues you might encounter with RBCs and how to troubleshoot them effectively. First up is decreased efficiency. This can often be caused by organic overload, hydraulic overload, pH problems, or low temperatures. To address this, you might consider improving pretreatment, adding an additional RBC unit, removing any bulkheads, recycling effluent, or adjusting the pH to optimal levels. Next, we have excessive sloughing. This usually results from toxic materials, pH fluctuations, or variations in flow and loading. To mitigate sloughing, you should aim to eliminate toxic sources, control the pH, keeping it in a safe range, manage flow peaks, and recycle effluent during low flows to stabilize conditions. Another common problem is white biomass development, which often indicates septic influent, high hydrogen sulfide concentrations, or overloads in the first stage. This can cause odors and organic loading issues early on. Solutions include pre-aeration, adding chemicals like sodium nitrate or hydrogen peroxide, pre-chlorinating, or adjusting baffling to improve flow distribution. Lastly, solids accumulation can happen if pretreatment isn't adequate. You need to determine whether the solids are grit or organic material. Then, remove the accumulated solids by improving grit removal processes or primary settling, which helps keep the system running smoothly. Throughout all these issues, understanding the root cause and applying targeted solutions is key to maintaining an efficient and healthy RBC system. Let's talk about the essentials for maintaining your RBCs. First, these rotating biological contactors have surprisingly few moving parts, which makes them easier to care for, but they still need regular attention. For example, chain drives, belt drives, sprockets, and rotating shafts should all be inspected and maintained according to the manufacturer's instructions or your plant's operation and maintenance manual. It's also important to protect exposed parts. Applying paint or grease to bearing housings, shaft ends, and bolts helps prevent rust and corrosion over time. Don't forget to paint motors, speed reducers, and other metal components to keep them well protected from the elements. Another key point is to inspect the covers regularly. They serve a dual purpose, protecting the organisms from weather extremes and helping contain odors, which is crucial for both performance and community relations. Monitoring the rotation speed is also vital. The typical speed is about 1.5 RPM, and keeping it consistent ensures proper operation of the system. Finally, remember to regularly check the underdrains. Removing any accumulated solids helps prevent blockages and keeps everything running smoothly. All these steps together form a simple, effective approach to maintaining your RBCs, and ensuring they operate efficiently over the long term.